Hello and welcome to part 4 of my video series on making artisan bread. In this part we're going to look at a little experiment that I ran to estimate the energy requirements for baking artisan bread at home. So I'm just going to walk through the process that I went through to make this estimate. I'm estimating how much energy was actually consumed when I baked it in my home oven, and then I estimate what the minimum energy is for this baking process, and using those two then I estimate an energy efficiency for the baking in my home, in my gas oven, what the efficiency of that process is. Okay, so the energy consumption of an 18,000 BTU per hour Frigidaire gallery gas range oven, that's the unit I have, was estimated by monitoring the oven's burner duty cycling over the course of the heat up and the baking periods. I used a photoresistor that was placed on the under oven storage drawer, or in the under oven storage drawer, and in proximity to the oven burner, facing it, such that an Arduino Nano could monitor the burner state, be it on or off. So it wasn't picking up the heat, it was actually the light created by the burning flame. Used the photoresistor with another resistor to make a voltage divider, fed it to the analog input of an Arduino, and the voltage changed sufficiently between when the burner was on and off that I could determine the state of the oven at any time. Based on the oven specifications, it was assumed that 18,000 BTU per hour of heat was being delivered to the oven. This is equivalent to 5,275 watts. Oven on-off data and timestamp were streamed by the Arduino to a computer over USB and logged to a file using a Python script. Excel was then connected to the ASCII data file using data source features in Excel. The data was imported and then analyzed, including computing the total joules of energy delivered by the gas range. Here's some visuals of my setup. I apologize, I don't have a picture of the photo sensor, and it's set up near the gas burner. On the right is the Python script, and in the lower right window is the data that's coming in over the serial or the USB from the Arduino. On the left is the Arduino Nano. I added a little OLED display as well, so I had some real-time data being displayed additionally. And in the center is the Excel file that is pulling the data from the saved ASCII text file and then processing that. Here's a zoom of some of that data. You see on the top is the oven state. It's either on or it's off. The horizontal axis is time in seconds, and the lower graph is the accumulated total joules of energy. So I'm essentially just integrating the top graph by scaling it by 5,275 joules per second, which is the heat rate for an 18,000 BTU per hour oven. So the oven is preheated at 495 degrees F. The pot loaf, that is the loaf that is put in the cast iron pot, is added at 1985 seconds. The baking stone loaf is added at 2087 seconds. And then after 15 minutes, the oven temperature is reduced to 380, and that happens just after the 3,000 second mark. Finally, the pot loaf is taken out at 4,768 seconds. Notice that at 3,000 seconds, the oven turns off and stays off for almost 1,000 seconds. That's because the set point was reduced from 495 to 380 degrees, and so the oven is cooling down but remains above 380 until this point here, just shy of 4,000, when the oven turns on again. The total energy delivered after the 4,800 or so seconds of baking is 13,000 kilojoules, or 13 megajoules. So the question is, how much energy is minimally required to bake a loaf of bread? So it's at least has to be sufficient energy to overcome the latent heat of water vapor escaping the loaf. So I assume that I measured the loaf before it was baked and afterwards, and reckoned that the net loss of weight, of mass, was due to water, just water loss. The loaf weighed 1,115 grams prior to baking, and 1,005 grams and then 975 grams after 15 minutes plus 30 minutes and 15 minutes plus 42 minutes respectively. So I used the total baking time in the end was the 15 minutes plus 42 minutes, and the net reduction in weight over that time was 140 grams. 140 grams of water evaporation corresponds to 316 kilojoules of energy, or of heat, for a 1 kilogram loaf. Now there was additional energy that was required to heat the unevaporated portion of the loaf, and I have more on the next slide, but basically the whole loaf had to be elevated in temperature before the 140 grams of water could be evaporated. This was estimated at 236 kilojoules. And then lastly, the Dutch oven in which the bread was baked also had to be preheated, and it was preheated all the way up to the 500 or 495 degrees. That was estimated at 637 kilojoules. I don't have any more information on that, but basically I weighed the pot. I know it's iron, cast iron. I looked up the specific heat, calculated what its thermal capacitance was, and then calculated the joules of heating based on it undergoing a temperature rise from room temperature up to 495 or 500 degrees F. So thus the total theoretically minimum energy required to bake a single 1 kilogram loaf of bread in a Dutch oven is approximately 1200 kilojoules, or 1.2 megajoules of energy. Here's a little more detail on estimating the thermal energy stored in a baked loaf of bread. I considered the two primary ingredients being wheat and water. I got their specific heats. When I made the batch of dough, I was measuring the ingredients individually, so I was able to determine the approximate weight of water in the dough and the approximate weight of wheat. And then I calculated the thermal capacitance of the wheat and of the water, and I combined them together for a total dough capacitance of 5.9 kilojoules per degree K. Then it was assumed that all of this loaf underwent a 20 degree C up to 100 degree C temperature rise. And I'm not sure that this is completely accurate, because I don't imagine that the dough at the very center of the loaf reached boiling point. So, this is just an estimate, but it would be, if anything, I think it would be less than this. I took half of that amount of energy because I'm doing 2 loaves here, and I'm assuming in this case both loaves are being baked in a Dutch oven. No, this has nothing to do with the Dutch oven, sorry. So take half of that amount and I get 236 kilojoules of additional stored energy in a loaf of bread. Okay, so the final result here, this is the last slide, is that I measured 13,000 kilojoules of energy that was used by my gas range during the baking cycle. The theoretical minimum energy required to bake 1 kilogram loaf of bread in a Dutch oven is about 1,200 kilojoules per loaf. And if I assume that I'm going to bake 2 of those, I could have done the same experiment but actually baked 2 loaves, both in Dutch ovens. I would have needed minimally 2.38 megajoules for both of these loaves. And that results in a thermal efficiency, energy efficiency of 2.38 over 13, or about 18.3% efficiency. So of the 13 kilojoules that were used, more than 10,000 kilojoules of that energy just went up through the vent of my stove and heated our house, which I could then calculate, well, to extract that using my air conditioner and knowing estimating the efficiency of my air conditioner, that would have been additional energy, significant energy required from the electrical service to my house to deal with that heat. So my interest here is in considering, well, is there a better oven that we could design that would save significant thermal energy, wasted energy, and still create yummy artisan bread that's baked in a Dutch oven? All right, well, thanks for watching. Hope you enjoyed it. Bye for now.